Hello and welcome back to the system design series. Key value store is a simple storage system which is very performant. In key value store, we store the values in terms of key and its corresponding value so that we can fetch the value very fast with the help of the key. In this session, we will start with a very basic design and we will enhance it so that at the end of this session, we will be able to design a resilient key value store. There are lot of real-time key value stores present in the market. Cassandra, Redis, DynamoDB are few of the examples of key value store. To design key value store in this session, let's refine the requirement first. We have to know what will be the data type of keys and values. What will be the size of each key values. How many key values will be added in the system per day? What is the retention period of the data? These are the few important questions we have to ask before designing the key value store system, because answer to these questions influence the design of the system. For simplicity, in this session, we will assume that the data type of key and values are something like integer and string. The size of each key values are of 1 KB. Let's assume there will be 1 billion references per day. When I am telling references, it can be a read request or a write request, and the retention period is of 1 year. With these assumptions, we will start designing our system. As we are ready with our requirements, let's do a rough estimation or back of the envelope estimation for this system. Remember, back of the envelope estimation is very important for any system design problem. With the help of this estimation, we can take critical design decisions. Let's calculate the QPS of the system. QPS is nothing but query per second. If you are not aware about QPS, please watch my previous video where we have discussed QPS in detail, or back of the envelope estimation as a whole in detail. We know our system load is 1 billion references per day. So it will be 10 to the power 9 by 10 to the power 5. If you are not aware how we are converting this to 10 to the power 9 by 10 to the power 5, I would highly recommend to watch my back of the envelope estimation video where we have discussed it in detail. So it will be 10 to the power 4 requests per second. Let's estimate the storage for this system. Assuming 20% is the write request, that means 20% of 1 billion references are the write request where we will be adding a new key values in our store. Hence, per day we will be storing 2 into 10 to the power 8 key values. What will be the size? 2 into 10 to the power 8 into 10 to the power 3, because size of each key is 1 KB. This boils down to 0.2 TB. So every day we are adding up 0.2 TB worth key values in our system. Assuming 1 year retention, in a year 0.2 into 365 TB or nearly 73 TB of data will be there in our system. Hope you have realized how, based on the requirements, we are estimating the queries per second and the storage requirement for a new system. We will see the importance of back of the envelope estimation while taking few critical decisions while designing the system. So, very initial design of a key value store could be something like this, where we have a single machine like this. This server will have large primary memory where we will use some map of integer and string. Once our primary memory is full, we will perform some eviction policy to move the key value pair in the secondary storage. So our clients can have read request or can have write request. In case of read request, client will pass the key and we will return the corresponding value from our system. In case of write request, user will pass key and value, and in this server we will be storing key and values in our primary memory initially, and once primary memory is full, we will perform some eviction policy and move the data to the secondary storage. This system will work for small number of key values without any issue. However, what are the disadvantages of this initial system? It's a single point of failure. We have limited storage space in a single server, and the estimated load is very high, which is 10 to the power 4 requests per second. A single server will not be able to handle this high load. So these are the issues what we need to solve by refining this initial design. Obviously, we need multiple servers to handle the high load, to increase the overall storage space, and to avoid single point of failure. Now, in the refined system, let's assume we have 4 different servers where we can store the key values within map. Now, what will happen? Our user will pass the key and value. Now the question is where this key value will go. Will it go to server 0 or 1 or 2 or 3? To solve this, we will calculate hash function of the key and then perform modulus operation by server number. This is a simple approach. So what we are trying to do here is to identify a specific server among these 4 servers to store the corresponding key value what user wants to store in our system. To identify the server, we can use some hash function and apply it on the key, and finally perform the modulus operation based on the server numbers to identify a specific server. So this result will be either 0, 1, 2 or 3 because we are performing modulus operation by the server number. In this case, it will be 4. Let's assume the key user wants to store is going to server 1. Similarly, the hash function of key, if it is divisible by 4, it will go to server 0. Hope you have understood the concept. However, the problem of this approach is what happens if the server 1 goes down? What will happen if we add some additional servers? For the first issue, 2 cases can arise. One, if the server goes down, we lose data. Second, based on our hash function calculation, there will be few keys which will try to store into server 1, but in reality server 1 is not present. Hence, as and when some server is going down, we have to modify the number of servers here in this calculation. For the second problem, if we keep the calculation same, that means the number of servers same, which is 4 in this case, the additional servers what we will be adding in the system will not be referenced. Hence, the additional servers will be empty. So, we need to modify the number of servers in the calculation. But in real-time system, at any point of time, the total number of servers may change. Hence, we need better design. We have seen the exact same problem while designing consistent hashing. Consistent hashing is a standard way to solve this problem. If you are not aware of consistent hashing, I have a video in the same playlist, you can refer the same. Hence, in the refined design, we want to use consistent hashing where there will be an imaginary ring and all the servers will be placed into the ring. As and when the new key is coming from client, some hash function will be applied on this key and it will be placed into the ring, and as per consistent hashing technique, this particular key will be stored into the clockwise nearest server. In that way, even if one server is going down, still the key will be stored into the clockwise nearest server. Hence, we don't have to change the calculation as and when one server is going down. It will be automatically handled into the system. This technique is known as consistent hashing. In this session, I will not go into the details of consistent hashing because I have a dedicated video for it. You can watch the same. Now, question is, if this particular server is going down, all the data or the key value pairs stored in this server will go away as well. So we will be losing data. However, as a key value store, we cannot afford to lose this data because it will degrade our client's faith on this system. What is the solution for this? Solution is replication. What we can do is we can store the same key value into multiple servers so that even if one server is going down, the same key value will be present in other servers. In that way, even if one server is going down, we will not lose any data. However, replication in a distributed system leads to inconsistency. We will see how. Let's assume the same key is present in multiple servers. If we want to change this value, let's say now we want value v2 for key k1. We have updated the value of the key k1. The same v2 value should replicate here as well. That means wherever we have replicated one key value, if any changes comes into value of that key, the modified value has to be replicated all the other places. Then only we will have consistent value across the system. In distributed system, we have something called cap theorem. Cap theorem is a principle used in distributed system to describe the trade-off between three key properties. One is consistency, availability, and partition tolerance. According to the theorem, a distributed system can achieve at most two of these three properties simultaneously, but not all three at a time. In case of consistency, every read request returns the most recent write or an error, meaning that all nodes in the system have the same data at any given point of time. If a read is performed after a write, the read will reflect the changes from that write. That means whenever there is a change in value, all the replicas of that value has to be modified. Then only consistency will be there in the system. On the other hand, if every request receives a response, but the response does not guarantee the most recent data, then we will tag the system as an available system, but not the consistent one. What about partition tolerance? The system continues to operate even if the network partition occurs, meaning some node or parts of the system is not able to communicate with other nodes. Even then system is up and running. We call it as partition tolerant system. Remember, partition tolerance is very important for any distributed system. Hence, a distributed system can have CP or AP, but not CAP. What is the meaning of it? The system that favors consistency and partition tolerance but not availability is known as CP. On the other hand, if the system favors availability and partition tolerance but not consistency, then the system will be of AP type. Hope you have realized what is cap theorem and why it is important in our case. If we want to make this system AP, that means if we want to favor availability over consistency, then we do not have to update all the replicas during a write operation. We can defer the update. On the other hand, if we want to favor consistency over availability, then we will perform write through operation. That means as and when one key value is getting modified, all the replicas has to be modified, then only we will send the acknowledgement for the write operation. In that way, we will ensure that all the replicas has the latest value in case of consistency. Based on the use case, we can either prefer availability or we can prefer consistency. For our use case here, we will be using a hybrid among consistency and availability known as quorum consensus mechanism. This mechanism used in distributed system to ensure that a majority of the nodes agree on the state of the system before making a decision. the idea is to prevent inconsistency that can arise in case of an available and partition tolerant system. Here we set a quorum size. Let's assume it is 3. That means whenever there is an update in the data, at least 3 replicas has to be modified or updated before sending the acknowledgement to the user. Similarly, we can set read quorum as well. So quorum can have write quorum and read quorum. Read quorum is the minimum number of nodes that must agree on a read operation. If we set it to 2, then at least 2 nodes must have same value, then only we will send the value to the client. If the write quorum is 3, then at least 3 replicas has to be updated before sending the acknowledgement to the client. So higher the quorum value is, higher the consistency will be in the system. If the quorum value is very less, then the system will be available but not consistent. So that means quorum value is the lever what we can set to tune the level of consistency in the system. If we set quorum value as 1, then the system will be available and partition tolerant. On the other hand, if we set the quorum value as total number of replicas per key values, then the system will be consistent and partition tolerant but not available. Hence, quorum value will be between number of replicas and 1. Based on the quorum value, the system will be either consistent. If we go this side, system will be consistent. If we go this side, the system will be more available. Hence, using quorum value, we can intelligently make a system either more consistent or more available. Hope you have realized how quorum consensus mechanism is helping us to design a system which is in between consistent and available. Let's now discuss few additional points related to a key value store. Quorum consensus mechanism makes a system eventual consistent. Why? Because though based on the right quorum we will update subset of nodes, there will still be few nodes which will hold the older value, and eventually based on a number of algorithms, gossip protocol is one of them which ensures eventual consistency. That means over the period of time all the nodes will have the up-to-date value. On the other words, initially based on your quorum value, few replicas will be updated with the latest value. The other replicas of that same key will be updated eventually with the help of gossip protocol. I'll not go into the details of gossip protocol. You can read it from internet. Eventual consistency also uses vector clock for concurrent updates. You can learn about vector clock from internet. Now understand the last point. Our retention period for the data is of 1 year. What will happen if all the primary memories of every server are filled up with key values? We need to perform something called eviction. In eviction policy, data will be moved from primary memory to secondary memory. For key value store design, even if we are keeping the data into secondary memory, fetching the data or indexing the data has to be fast. We can use some data structure called ssTable for fast retrieval of the data. ssTable means sorted string table. In our subsequent session, we can discuss about gossip protocol, vector clock, sorted string table in details. Let's summarize the session now. In this session, we designed a key value store. Key value store is a very simple and performant storage system where we save key and values. Cassandra, Redis and DynamoDB are few prominent examples of key value store. We started with requirement gathering where we got some more information or additional information of the system to be designed. Using those information, we estimated QPS and storage requirement of the target system. We started with a single server approach where we thought of keeping key values as map in the primary memory of the single server. However, based on the QPS estimation, we realized a single server will not be able to handle 10 to the power 4 requests per second. Apart from this, a single server is the single point of failure. It has limited storage space as well. From our back of the envelope estimation, we realized we need at least nearly 73 TB of storage space to keep key values of 1 year as per the requirement. Hence, looking at the issues, single server concept will not work. We refined the design by adding a number of servers. Instead of single server, we refined the design by adding 4 different servers. We used some hash function and modulus operator to identify the server where a specific key value will be stored. Now, there were 2 critical questions. What happens if the server goes down? What happens if we add additional servers? The case where server is going down, we lose the data and our hash calculation has to be modified because instead of 4, now we have 3 different servers. Similarly, even if we add additional servers, we need to modify the hash calculation. In order to solve that issue, we came up with the consistent hashing approach, where in a single imaginary ring, we will place all the servers based on some hash function. We place all the key values based on the same hash function, and the key value will be stored within the server which is clockwise nearer to the key value. For consistent hashing, I have a dedicated video what you can refer for details. Our application, which is following consistent hashing, is up and running even though one server is going down. However, we need to replicate the data, otherwise we will lose the data if one server is going down. Hence, replication is the critical requirement for our design. A new problem arises. In a distributed system, if we replicate the data and the same data gets updated, we need to update all the replicas. Otherwise, our system will not be consistent. Hence, cap theorem came into picture. We discussed about cap theorem. We realized what is consistency and what is availability along with partition tolerance. We realized if we want to make our system consistent, we have to perform write through operation. That means once all the replicas gets updated, then only the acknowledgement of write operation will be sent. But this will be time consuming. The other approach is AP, where we can defer the replica update. In that case, though our system will be available, however, there can be the cases where our client will get older value of a specific key and not the latest value. We have to trade off between consistent system and available system. In our case, we came up with some hybrid approach, which is quorum consensus mechanism. Using quorum value, we can regulate the consistency of our system. If the quorum value is equal to the number of replicas, then our system will be highly consistent system. On the other hand, if quorum value is 1, then our system will be highly available system, but it will not be consistent. So our final design is to use consistent hashing with quorum consensus mechanism, which gives us a resilient design of key value store. Apart from this, we also have discussed few additional points such as eventual consistency. With the help of gossip protocol, we can have eventual consistent system which is distributed in nature. For concurrent update of the value can have conflicts. To resolve the conflicts, we can use vector clock. As we will be storing nearly 73 terabyte of data into our system, it is impossible to keep all the data into the primary memory of each server. We should keep the data which are older and unused for a long time secondary memory. However, keeping the performance in mind, we can use a very well-known data structure called ssTable or sorted string table, so that even if those key values which are present in secondary memory are getting referenced or indexed, we get the value very fast even from secondary memory. Hope you have realized how step by step we have refined our design and finally designed a resilient key value store system. Few concepts like gossip protocol, vector clock, ssTable can be discussed in our subsequent sessions. If you have learned something new, do not forget to like this video. If you haven't subscribed my channel, please do so. Thanks a lot for watching this video.